All right. Hello, everybody, to our next session in the Laws of Nature series. As probably most of you know very well, it's tradition to say a couple of words about this Laws of Nature series and then get to the talks that we have scheduled today. So the Laws of Nature series is basically a discussion series of online seminars about physics, about philosophy, and about mathematics. And I think especially this series that we have planned, we have a quite broad spectrum between the very mathematical physics to the very philosophy and in between physics talks. So we had already our first session in October with Paula and with Sheldon Goldstein. And today we continue with Flavio Mercati and Julian Barber. We're very happy that we could have gotten these distinguished speakers for our next session. A couple of words about us, who organizes this. So that's mainly Angelo Bassi from the University of Trieste. That's Ward Struve from the KU Leuven. And another name here that's missing, who joined now the organizers, Paula Reichert-Schirmer, is also from the LMU Munich at the moment. And yeah, we hope to provide you well with a nice program. So I would say, because these words I think we say in each and every time, I would say let's start right into the session. Paula will moderate as usually the session. She will give us a couple of yeah, somehow quotation mark rules how this session will go about, and introduce the speakers, and maybe also lay out what's going to happen in the discussion session later. So Paula, I hand over to you.
Okay, thanks. So welcome everybody to this session. Today's title is, or today's motto is, the shapes of things. And this indicates already that we talk about shape dynamics, more generally about relational physics, and well, and the most recent formulation in terms of shape dynamics. And I'm happy that we have two experts here today, Flavio Mercati and Julian Barber. And before we start, just let me remind you that during the talks, if you want to ask a question, just write it into the chat and we see if we find the time to ask it. And then after each talk, there will be 15 minutes for questions where you can just raise the hand and I call you, and then you can ask it directly to the speaker. So we have two talks of about 45 minutes and 15 minutes questions. And in the end, we have 1 more hour to have a more general discussion on different topics, general topics of shape dynamics. Okay. So let us start with the first speaker, Flavio Mercati. He's from the University of Burgos. You know him maybe from the book. He has written the book Shape Dynamics, and he's an expert on this topic, both in Newtonian and general relativity. And today we'll talk about singularities and the most recent results on whether or not we can pass through the singularities. Thank you.
Thank you very much, Paula. And let me thank also Dirk and Angelo for organizing this and inviting me to this nice event. Let me share my screen here. Full screen mode. Can you see well?
Yes, perfect.
Okay, thank you. So I will talk about singularities and how the shape dynamical point of view on classical general relativity can inform us on the true nature of this property of gravity. And in particular, I wrote in the title determinism because I will not attempt at resolving the singularity as could be expected of a line of research that attempts to say something new about gravitational singularity. because the space-times that in some appropriate situations will emerge out of the solutions to general relativity that I've been considering are singular. There is the singularity is still there. The question is whether it preserves the property of classical physics that we call determinism. And that is where shape dynamics has something to say that I consider new. Here's a list of the work that I've been doing with many collaborators, mainly Julian, of course, and Tim Kozlowski and David Sloan, and more recently my students Martina Adamo and Rishab Jha. And I will repeat this later. But let me start with the current picture of singularities in classical general relativity. This is a Ferrous diagram represented as a sort of ancient map. And this is what it is. The Ferrous diagram is a map of a space-time that informs us about essentially the causal properties of that space-time. Every point corresponds to a different region, spherical region in a spherical symmetric space-time. And singularities are a region where we really don't understand how to do physics. The standard framework in which one understands operationally the meaning of space-time and how it interacts with the other fields and how to do physics on it kind of breaks down in this region. So I represented it like one of those remote regions, or rather far from Europe regions that ancient map makers would suggest that they are home to mythical creatures, lions or dragons. To be more precise, the precise sense in which I'm saying that there is a problem with the way we normally do physics near a singularity is well explained by this quote by Stephen Hawking in a 1976 paper. He says that the singularity can be regarded as a place where there is a breakdown of the classical concept of space-time as a manifold with a pseudo-Riemannian metric. Because all known laws of physics are formulated on a classical space-time background, so far at least, they will all break down at a singularity. Okay, but what is the problem? So he says that this is a great crisis for physics because it means that one cannot predict the future. One does not know what will come out of a singularity. So this is the expectation among most physicists that a singularity, there are many aspects of a singularity that are problematic. The one that I will be focusing, because also I consider the most dramatic departure from the normal way we do physics, is this: what Hawking defined as a breakdown of predictability. So the fact that one cannot predict the further evolution of fields, observables, the metrics, and so on after a singularity. Sorry, I have a phone here that I don't know how to stop. I think we'll have to live with this, unfortunately. Okay, so here I have a slide on the common expectation, the most upheld expectation about how people think that a way forward from gravitational singularity might be possible. It is through quantum effects. If someone proposes a quantum theory of gravity, one of the first things they will check essentially is whether there is some more resolution of singularities. This expectation is well motivated because something like that happens in in quantum electrodynamics. In classical electrodynamics, there is a observable property of certain field configurations that becomes singular when we consider a distribution of charges that becomes point-like. So when we collapse, for example, a sphere of constant charge, what is called the self-energy of the electric charge, which is really the energy that is stored in the electrostatic field, diverges when the charge is shrunk to a point. In quantum electrodynamics, this is solved, this singularity is resolved because of the uncertainty principle, because really there are limits to how much one can focus this distribution of charge. And analogous calculation for the self-energy of a point-like charge performed in quantum electrodynamics is something that involves sum over Feynman diagrams, a standard calculation in advanced courses in quantum physics, and it gives a finite result if treated carefully. However, so many authors try to argue that this or that quantum theory of gravity resolves gravitational singularity with an analogous phenomenon that is essentially due to quantum uncertainties. However, I will argue that a point charge and a gravitational singularity are quite different objects. Just to mention one striking difference is that I have to assume by hand here that there is a distribution of charge that I try to compress infinitely much. It's not clear that there is that this comes out of as a solution, a classical solution to the theory. In general relativity, there are the Penrose-Hawking singularity theorems that they state that given rather generic initial conditions, and initial condition that is collapsing essentially, a singularity will form on its own because of the equations of motion. So it's not exactly the same. Let's recap what the things that are, what is that is singular out of the gravitational singularity? Well, several things. For example, in a cosmological singularity, you have the volume, which is the size of a certain region in a certain foliation, the spatial size of such region. That goes to zero at the singularity. So the distance between points that were previously space-like separated will become zero. Then there are eigenvalues of the energy momentum tensor that diverge, become infinite. And the most popular way to detect a singularity is to study curvature invariants, which, if they diverge, appropriately define curvature invariants, so things that are clearly not dependent on the coordinate system. That is a sign that there is a singular space-time. But the question I will ask is, do these things make the dynamics ill-defined? In a sense, is it because of these things going to infinite? Do we have to give up classical determinism, or is there are they two separate things? There might be solutions that keep their deterministic nature, that continue through a singularity, even though at a certain point on the solution, certain quantities go to infinity. However, it could be the opposite. It could be that these things going to infinity violate the basic assumptions about the differential equations that define your theory, and therefore will not let you calculate how the solution evolves past that. it's not an obvious thing to check. So what do we mean with classical determinism? Well, if we have a discrete dynamical system, so there's a finite number of states and a discrete, a time evolving discretely there, determinism is the system will be deterministic if the law that defines it is. So if it's a Markov chain, it will not be. If it's any other dynamical system that uniquely predicts the future evolution, it's automatically embedded in the system. However, for systems with continuous independent variables, so whose dynamics is defined by differential equations, determinism is a more nuanced concept. It's more subtle. The problem is whether certain initial conditions satisfy existence and uniqueness theorems. In the case of hyperbolic partial differential equations, like the case of general relativity, this is quite a tricky issue. If we have a situation in which we have a finite number of continuous variables, so for example, a classical mechanical system, like point particles in Newtonian dynamics, for example, the existence and uniqueness takes the name of the Picard-Lindelof theorem for ordinary differential equations. This is a much simpler situation than partial differential equations. Now, there is a third complication. It's the fact that GR is a gauge theory, in the sense that there are redundancies in the description. If you describe it with a form metric, there will be degrees of freedom that are not physical. They are associated to the ability to change coordinates, essentially. So if we are interested in the determinism, we should be talking about the Hamiltonian formulation of GR. And this is a theory then that is known as a gauge Hamiltonian system, which has constraints. This is how its gauge nature manifests itself. And so not all degrees of freedom are physical. And if determinism fails, it has to fail for what regards the observable, the physical degrees of freedom. If something goes wrong with the gauge degrees of freedom, it's not a problem. This brings us to the question, what are the physical degrees of freedom of GR? Because it's by no means a simple matter. Behind it, there's a lot of history of mathematical physics. I think the approach that really allows us to identify what we call a reduced phase space, so a set of physical degrees of freedom for general relativity, is what is known as the conformal method, or York method, because Jimmy York was the one who contributed the most to it, but it has a long history, beginning with Andrei Lichnerovich in the 40s, Yvon Chokret-Brouat, Jimmy York himself, and at last the near Omuraco, Julian's collaborator, who recently passed away. So this approach allows to recast the initial value problem, so the constraints that a solution of GR has to satisfy in order to be a solution, into elliptic partial differential equations rather than hyperbolic. If you have an elliptic PD, existence and uniqueness theorems are available. And this happens whenever there is a particular way to colligate space-time known as constant trace extrinsic curvature. So this extrinsic curvature, which measures how space expands in space-time, has to have a constant trace everywhere. So it's known as CMC collision. In such a collision, it turns out that the physical degrees of freedom, the ones that are not gauge, are conformal three geometries. So three geometries, if you want, three metrics, modulo spatial diffeomorphisms, and modulo local conformal transformations, or wild transformations, as some people call them. Of course, also the conjugate momenta, which are the velocities associated to these objects, and they are transverse traceless tensor densities. Shape dynamics takes its initial inspiration from this. Is the proposal to take seriously this input from the conformal method and really work under the assumption that these are the true degrees of freedom of gravity, and nothing that is not conformal essentially will be a physical observable, but it will rather be gauged. So, for example, the volume that I mentioned here of a cosmological solution, it will be gauged in a shape dynamics description. So if it goes to zero, or there are its evolution is not unique after a certain point, that is not in principle a problem for shape dynamics. So the question is this: we can express physics. The shape dynamics full description of general relativity is sees the evolution, the dynamical evolution, as the rate of change of one shape degrees of freedom, so conformal invariant degree of freedom with respect to the other. Then the York method, which in shape dynamics becomes a sort of dictionary to translate from the conformal invariant description to the usual space-time description. It provides us with a map from such a history of conformal tree geometry to a four-dimensional space-time. And then after this map is applied, one has curvature invariance, volumes, energy momentum tensors, and so on. Now it's clear what we want to know. Is it the shape evolution itself singular, or is it in the map, the singularity? Is it because we're trying to map conformal degrees of freedom to space-times through a map that becomes singular somewhere? If the latter is the case, then determinism, classical determinism, is preserved. I can continue my evolution through a singularity in a unique deterministic way, and then the space-time that this maps into won't be regular. There will be two blocks of space-time that will be welded together according to a precise law in a unique way, because the underlying dynamics is deterministic. So how to test this? We need, of course, to find a simpler description of singularities. Approaching the problem in full generality might be too much. In ninth starting point is provided by us by a conjecture by Belinsky, Kralashnikov, and Lipschitz in the 70s, who observed that near a singularity, essentially the spatial derivatives that appear in the Einstein equation become suppressed with respect to the temporal derivatives. And so technically, one should talk about velocity-dominated equations, which are the equations of motion of general relativity, in which all spatial derivatives are removed, are set to zero. And then the technical result is that every solution to Einstein equation approaches a solution of the system, this velocity-dominated system, near singularity. There is a lot of numerical evidence in favor of this conjecture. And actually, there is a rigorous kind of proof by Anderson and Randall in 2001 that involves a massless scalar field, or in general, a stiff fluid source. If such a field is present, then we have a proof that every velocity-dominated equation corresponds to the limit of a certain solution to the full field equation. So the velocity-dominated equations are not partial differential equations anymore. they are an infinite collection of ordinary differential equations because there's only derivative with respect to time and nothing else. But there is one such system of ODEs per point because the fields are still dependent on the coordinate, on the spatial coordinates. What is this system of ordinary differential equations? Well, if we assume that we have a spherical topology, so the topology of a three-sphere, these equations are those that you get by considering so-called Bianchi I universes. So you assume a spatially homogeneous ansatz, and what you get is 2 degrees of freedom. This is what people call a mini or maybe midi superspace ansatz. Of course, no, the homogeneous modes satisfy the same ordinary differential equations that you get in the velocity-dominated system. That makes sense, no? The degrees of freedom that the system that describe the system are 2 shape degrees of freedom called Misner variables. I call them x and y because I can put them on a plane, and the volume, the volume of my three-sphere. These 2 shape degrees of freedom define the anisotropy of my three-sphere. So when they're 0, the three-sphere has the round metric, the spherically symmetric geometry. When they're non-zero, it is like a 3-dimensional ellipsoid, if you want. We can introduce conjugate momenta to these shape and volume degrees of freedom. Tau will be the so-called York time as the conjugate momentum to the volume. And the system reduces to only one constraint. All the other infinite amount of the constraints that define general relativity will be trivially satisfied. And this constraint really looks like essentially the Hamiltonian of a point particle with a certain potential. This is a normal kinetic term. There will be a kinetic term for the volume York time part that has the opposite sign, hence the nature, the hyperbolic nature of general relativity. And the potential term will be this complicated function, the sum of 3 copies of f from different combinations of x and y. This is f, that is an exponential form. And it will all be multiplied by this power of the volume, which acts as a sort of coupling constant for this potential. Let me quickly describe the dynamics of the system. This is the potential, and the 2 things we need to observe of the potential. It's triangularly symmetric. It's symmetric under rotations of 120 degrees. And it's extremely steep because it's exponential. So if I plot it in a 3-dimensional plot, it will look almost like vertical walls, vertical potential walls. So whenever the point particle is far from the wall, so the kinetic energy is much larger than the potential, the representative point on my shape space will evolve as a free particle. Whenever it approaches where the potential has the same magnitude as the kinetic term, there will be a bounce because the potential is very steep. So the particle will be reflected. Okay. So this is the qualitative description of the solutions. The solution will be near the origin of the Misner plane, so where the geometry is more symmetric, is more spherical at the center. And then if I evolve in the 2 time directions, there will be bounces. And the particle will start behaving like a free point particle, evolving, moving across lines, straight lines uniformly, and very short time bounces. These are called Kastner epochs, the straight line evolution, and these are called tau transitions when the particle bounces off the walls. Now, notice again that the volume multiplies the potential. The volume can be easily proven to be evolving monotonically to 0 in the two time directions away from the central one. So it's in future and past. All solutions, if I don't introduce stuff like a cosmological constant or something else, some method that makes the universe expand, the solutions will look like two big bangs with a big bound to the center. Okay, so maximum expansion and then a new big bang. Towards the two big bangs from the big bound, the volume will evolve monotonically to 0. Since the volume evolves to 0, the potential will be less and less strong. And therefore, so these are three pictures in which I plot the same solution over an interval of parameter time that is larger and larger around 0, okay? From minus to a certain value to plus a certain value. The further away from the central time, from the initial condition I go, the further this point particle away will evolve from the origin of the Meissner plane. So we'll keep bouncing more and more, but we will be zooming out of the origin. So we will explore a larger and larger region in my Meissner plane. So as t goes to infinity, intuitively the particle should spend more and more time closer and closer to the border of my Meissner plane, which is at infinity in these coordinates. So the singularity is when t goes to infinity in each time direction. Time here is just a parameter, it has no physical meaning. I reach the singularity at infinite time. So the singularity is a region in shape space. It is the boundary of my Meissner plane. Now, one question one could ask is, does the potential grow so small as d goes to 0 that at some point my particle never catches up with it and stops bouncing? No, it can be proven analytically that this does not happen in the case in which I have no other field other than the gravitational one. So there will be an infinite amount of bounces as I reach the singularity. Now, the singularity is a t infinity, but t is just a parameter, and in particular, it's not proper time. It's just an independent parameter. If I calculate proper time, the elapsed proper time from any finite value of t to t infinity, it's finite. This is well known. The singularity of the Big Bang is reached in a finite proper time. It's not in the infinite past. Therefore, I have an infinite amount of bounces in a finite proper time. This, for the dynamics in shape space, is a singularity, and in particular, it's an essential singularity. It's similar to what I get when I take the limit of the sign of 1 over x as x goes to 0. Infinite oscillations in a finite region, and here the oscillations are much more periodic and complicated, but still you get the point. I explore an infinite region of my boundary of shape space in a finite amount of proper time. So this is what you call an essential singularity. And actually, in a paper with Paola here, we studied the analog of this sort of singularities in the Newtonian n-body problem. So Newtonian gravity acting on point particles. And total collisions are the analog of a Big Bang in that case. Well, it turns out that there too, total collisions is where all the particles collide at the same time at the same point. In this case, one encounters another essential singularity. And, there are two textbook examples of essential singularities we study in calculus courses. One is sine of 1 over x, the other is the exponential of 1 over x. Of course, they're related, but they're different. And this is what we find in Newtonian gravity, interestingly. Okay, so this slide is just to observe that in this case, so we have a singularity. The dynamics, there isn't a sense in which you can continue past it because of the essential singularity that really breaks the nature, the deterministic nature of ordinary differential equation. However, we argued based on also on previous papers like this by Anso Agnon that we should really think of the singularity as being in the infinite past, because there is an infinite amount of evolution in shape space between any finite point and the singularity. And therefore, if time has to be understood as a measure of change, there has been an infinite amount of it between any finite point and the singularity. Proper time is finite, but proper time is a bad measure of time near a singularity. It's good when you have a small space-time and a small object that follows a geodesic. Then the small object, its internal degrees of freedom, they could be the degree of freedom of a clock, will evolve and they will march in step with what is measured by proper time along a word line. For example, the word line coinciding with its center of mass. But clocks are extended objects by their very nature. Otherwise, they couldn't have internal degrees of freedom that can count time. And any extended object will be torn apart by very strong tidal forces near the singularity, because the dynamics becomes more and more dramatic. This evolution will tear apart the degrees of freedom of the clock and scramble them all over, and they will go through an infinite amount of evolution in what is defined as proper time according to the proper time read on a geodesic. So proper time is not really anymore a good measure of time in this case. We can argue about that if anyone is interested in discussing this. Okay, did we prove that determinism is dead? Not quite, because we also studied what Anderson and Randall considered when they proved the declare singularity, a situation in which you have some stiff matter sources. For example, the simplest example is a scalar field. Any other standard model fields will not be stiff, will not have the right equation of state to cause this behavior that I will show you. Only a scalar field with an appropriate potential, the potential that doesn't grow too large, too fast as the field goes to infinity. So anything that is not faster than an exponential will do. In particular, inflationary potentials for scalar fields will work. If you have a scalar field like that, that theorem that I mentioned, that there are an infinite amount of bounces because the potential, the point particle always catches up with the potential, fails, and there will be a finite amount of bounces in any given solution. After the last bounce, the solution will settle on a Kastner solution, so a straight line evolving all the way to infinity in shape space. Then, so it will be like this. A mass of bounces until a last bounce, and then the particle will shoot all the way to infinity with a uniform motion. If the dynamics is like this, then the singularity on shape space is regularizable. It's still a singularity, the volume is zero, the space-time is singular there, but the shape dynamics of the system can be continued through the singularity. To prove this, we have to go through a further complication, which is that the fact that we have to extend our configuration space. In particular, we have to observe that the GR description of gravity is orientation blind. The action, Einstein action, is invariant under change of orientation of my spatial hypersurfaces. However, a description based on, for example, dry binds or peel binds will distinguish between the two orientations, or that I can define on my spatial hypersurfaces with the determinant of the dry bind. So if I have to describe all possible orientations of my spatial hypersurface, I have to just double up the shape space. I have, instead of one linear plane, two copies of it, one for each orientation. This is okay in normal situations when there are no singularities. I could be on either. I have to choose my sheet, and I will live all my life there. My evolution will all happen on one sheet. However, here we're reaching the boundary of these planes because we have a singular solution. So what we do, and this is something that is just the simplest extension of the dynamics of general relativity that we see. It's not necessarily the unique one or the only way to do this, but it's just simple. We define a different topology for our configuration space, for our shape space. We solder the two planes, the two Misner planes, at the boundary. And we do this by using what is called the Gnomonic Projection. This is simply, I take the two planes, I put them parallel to each other in a two-dimensional space, and I define the sphere that is tangent to both. Then from the center of the sphere, I trace the line and to a point on one of the two planes. The intersection between this line and the sphere is my point on the sphere. This way, I map a whole plane to a hemisphere, the other plane to the other hemisphere, and I have soldering conditions that define a global topology for shape space. Okay, so I have a rule to go from one orientation to the other smoothly, essentially. This change in topology is everything here. It really allows us to define a smoothness structure at the boundary of shape space, and therefore a notion of continuing smoothly, a solution smoothly through it. So, for example, take this is a shape space for one orientation, shape space for the other orientation, and the shape sphere for both orientations. And I plotted the potential of Bianchi IX dynamics on both planes and on the sphere. Now take a Kastner solution. We said it's a straight line on the plane. For example, this one, the fixed orientation. This is easy to prove that it maps to a semicircle, a half a great circle on the sphere that goes from one point on the equator to the other, to the opposite one. Obviously, according to the topology of the sphere, there is one smooth way of continuing this solution through the equator, and it's by completing the great circle. Interestingly, this great circle, this other half of the great circle, the green one, maps to a Kastner solution and the other oppositely oriented Misner plane, which is completely different from this one. They're in a different place with the different values of the potential, etc. So a Kastner solution can be continued uniquely through the singularity. The question now is whether the full dynamics of Bianchi IX equations does that, because there are degrees of freedom that are shape degrees of freedom, in the sense that they can be expressed as the derivative of one shape degree of freedom with respect to the other, or further derivatives that are encoded in the Bianchi IX solution, but they are all the same for the Kastner one. So it's not obvious that one can that the same result works for the full dynamics of Bianchi IX. It turns out it does, because we can write the differential equations that define the dynamics in appropriate variables and prove that the Picard-Lindelof theorem works there. Essentially, you prove that the right-hand side of your differential equations is Lipschitz continuous. And so what we get is a situation in which on the shape sphere, you have a complicated dynamics of great circles interposed with bounces, which at some point will undergo a last bounce and will settle around a Kastner solution, so a single great circle solution. It will reach the equator, which is the boundary of shape space at the singularity, and will continue uniquely and then evolve into its own Bianchi IX solution with opposite orientation. Now, one could not agree with this, but a argument based on essentially simple statistical mechanics assumptions could lead us to argue that a the physical notion of time, what we observe, in particular of arrow time, will point in opposite ways on the two sides of the Big Bang. This is based on a paper with Julian and a team from 2014, which concerns n-body dynamics, but is still equally applicable here. If we set initial conditions at the singularity, then the system should, as it evolves away from it, it should develop all the other notions of arrow times, like the thermodynamic one, for example, for subsystems, away, pointing away from the singularity. So if we believe this, we don't have to, but this is a suggestion, then the emerging picture is that of two universes with opposite spatial orientation, with the oppositely pointing arrow times, that are glued at the Big Bang. Okay. All right. So I said that we require a scalar field, which some will frown upon this. I could argue that a scalar field is required by inflation in order to explain the present observations. Another argument that maybe we live in a universe in which there is such a scalar field is that you don't need a scalar field at all to have this dynamics. You just need to consider the first lowest order quantum correction to the Einstein action, and then you get what is known as the Starobinsky action, which can be rewritten as a scalar field minimally coupled to GR. Then you only have gravity, but quantum correction unlock a further degree of freedom, which is scalar. And it has a potential, and the potential is of this form. This potential is of the form that we need, has a slow roll phase, and so as the field goes to infinity, it grows much slower than an exponential. Furthermore, it sits right in the middle of current observational constraints from the cosmic microwave background and the early universe. So it's an interesting observation that maybe we live in a universe that is made like this, or at least quantum mechanics seems to require it, so that we have quiescence and we don't have an essential singularity at the Big Bang. So to rephrase, our best understanding of semi-classical gravity at and before the inflation epoch is a model that exhibits our property that can be continued uniquely to the Big Bang. So this is what we did regarding to cosmological singularities. We have further work on black hole singularities and gauge fields. How much time do I have left? This is a very short.
Yeah, you can go on for a few minutes.
Okay. A more recent paper with David Sloan focuses on black hole singularities, and it turns out that they can essentially be written as yet another cosmological model, homogeneous cosmology, because there is this formulation due to Kantowskiâ and Sachs, in which we describe the interior of a Schwarzschild space-time as a homogeneous cosmological solution with a topology of a two-sphere times the real line. So we are in a hypersurface, spatial hypersurface inside the horizon of Schwarzschild, and we describe the dynamics as we go towards the singularity. We have only one shape degree of freedom called W, and the Hamiltonian constraint is very similar in structure to the Bianchi IX one, except that it doesn't depend on two variables, only on one. So you have the volume part, the shape part, and the potential part, and the volume to the fourth third that gives the coupling constant between the potential and the dynamics. So the solutions all look like this in the space volume log of the volume versus shape degree of freedom. They are straight lines that then bounce off the potential wall and go into other straight lines, always at 45 degrees. Going in one direction, we reach the horizon where the Riemannian invariants are finite. In the other direction, because it's a coordinate singularity, in the other direction, we reach the actual singularity of Schwarzschild. So the similarity to the Bianchi IX system allows us to prove a continuation result pretty much along the same line. Interestingly, here there is no mixed master behavior, as Misner called it, no chaos, no chaotic bounces. There's only one bounce per solution. The rest, there is like automatic quiescence. I don't even need the scalar field here to prove continuability. And so proving continuation is trivial. However, since we want to describe the two, well, we want to have enough degrees of freedom so that it makes sense to talk about determinism. If there's only one degree of freedom, your shape space is a line, or in this case, a circle. Saying that my equations predict that as I reach the singularity, which is a particular point on the circle, I will continue following the circle, that's not very physical. There isn't much content in that statement. There isn't a shape dynamics of a one-dimensional shape space, because I need to describe the evolution of one shape degree of freedom with respect to another. That's physical. If there's only one degree of freedom, it can only evolve with respect to itself. It doesn't make much sense. So we do add some other physical degrees of freedom. The simplest thing, of course, is again a scalar field, but we could add homogeneities, gauge fields, etc. With the scalar field, we prove that not only we continue the equations of motion are satisfied Picard lead zeros there, but we can also predict the evolution of the scalar field past the singularity. So there is a sense in which determinism is satisfied for all degrees of freedom beyond the one shape that we have. This is a tentative picture of what's going on. This is the standard Ferrous diagram of Schwarzschild. This is the exterior. The red region is the interior of the horizon, which is all we can describe with this Kantowskiâ Sachs model. And the singularity is the space-like hypersurface here. When we add the other half of shape space, which has the opposite orientation, we essentially attach another Schwarzschild interior to the other side, where the spatial orientation is reversed. And presumably this would evolve smoothly also into another Schwarzschild exterior if we were able to go through the horizon. So, okay, I already anticipated this, but here I just say, look, to have a non-trivial shape dynamics, we need 2 degrees of freedom. So we have a scalar field, and we have again a shape sphere rather than a circle, and we have 2 planes, which with the Gnomonic projection we can get a global topology for all orientation shape space. Okay. So further work on black holes should focus on increasingly more realistic situations, and so adding other type of method by keeping the homogeneity answers, considering also that the fact that the Schwarzschild is an eternal solution, an eternal black hole, it doesn't include a description of how it forms through gravitational collapse. So we could include that, for example, the dynamics of a star collapsing, or a thin shell of dust, which is even simpler. And then the question arises, what happens to the matter when you cross the singularity and you're into this expanding Schwarzschild interior? Do you have like a white hole here, or what? And of course, then one would like to add inhomogeneities, because everything is homogeneous so far, and master, presumably in a perturbative scheme. And then we would really like to have something more generic, like a sort of something on the line of Heuristic theorems. Whatever matter I add that satisfies certain conditions, presumably some energy conditions, do I get go into an orientation flip region to the singularity? Last thing I want to say is that with my two students, Martina Adamo and Richard Ja, we've been studying also gauge fields coupled to Bianchi IX homogeneous cosmologies. The gauge fields themselves are homogeneous. And it turns out that one has three linearly independent, three independent shape degrees of freedom for the gauge field that are homogeneous on a Bianchi IX universe. So you end up with a shaped space that has one volume is not shaped. Then you have two Misner variables, the two-dimensional shape space of Bianchi IX, plus three components of the vector potential, which are three homogeneous shape degrees of freedom. And the Hamiltonian constraint is that of Bianchi IX plus two terms. One, two terms which involve the E, the electric field conjugate to A, and A. These two terms are different because one involves the volume. So when the volume goes to zero, this is suppressed. This is not. So this in principle would be a possible problem. It could invalidate the result. However, it turns out that this matrix that multiplies my gauge degrees of freedom goes to zero at the Big Bang. So as I reach the boundary of my linear plane, if I reach the boundary in any direction other than 6 special directions, which are the axes of symmetry of my shape potential that I showed you before, in any other direction, this will go to zero as I reach the boundary of shape space. So these are measure zero situations, these axes, and need to be treated carefully because they are regions where the gauge that we used to solve the diffeomorphism constraint fail. Why? Because they are the plane, the lines where you have a symmetry. Two of the eigenvalues of the metric are the same. And so it's not a really singular situation. It's another type of gauge singularity, if you want. Anywhere else, if you reach the boundary of shape space, the result that I showed you before is valid, unchanged. And so I think this is enough to prove the continuation result with the homogeneous electromagnetic field. Okay, these are details I don't want to go through, and the conclusions we can discuss if there are questions. I just wanted to show the last slide, which contains all the papers that I published so far on this line of research, and there's also a mention of my book published with Oxford University Press with a lot of details on shape dynamics. Thank you very much.
Thank you, Flavio, for this very nice talk. So I think this was very interesting. Please, if there are questions, we can now take questions. So you can raise your hand. Or maybe can I ask the first question? Dirk, you want to ask the first question?
Yeah, if you want to go, you're in the pole position to ask your question.
I can ask it second.
Okay. Now, I was just wondering, but it's mainly because I don't yet understand the shape dynamics so well. What is so special about the scalar field? Is it just a technical requirement that you need in this Bianchi IX space, or is it, is there something special like, I don't know, like with the Higgs field or?
The technical result is that if you have stiff matter, of which the scalar field is the only example of a fundamental field that does that. Of course, you can just assume a fluid that has a particular equation of state. Doesn't have to be a scalar field, but a scalar field is a way to embody this kind of equations of state with the presumably fundamental field. With it, the continuation result holds. Without it, we have an essential singularity. Then I argue that I think that there is something special with the scalar field, because observationally, it really looks like cosmology, in particular inflationary cosmology, is very well explained by a scalar degree of freedom being important during the early epochs of the universe. And so I would say there are indications that something like that exists. There is, of course, the Higgs field. However, its Higgsflation is at the moment not extremely powerful as regards its explanatory power for inflation. So people would say we don't think that the Higgs field is responsible for inflation, but the Higgs field is a scalar field that we already observed, and so far as we know, it's fundamental, and it has a potential that doesn't grow faster than what is needed for the result to hold. This is as regards observation. As regards fundamental physics, I would say that the Starobinsky model to me is very striking. From what we know of quantum field theory so far, the natural thing to do is to treat Einstein gravity as an effective field theory. An effective field theory has a lot of terms that are suppressed in the classical regime, The first order corrections to that is an action which contains a term that goes like Ricci scalar to the squared Ricci scalar. That is the model that Starobinsky studied classically. And it turns out to be identical to normal ordinary Einstein gravity, minimally coupled with a scalar field, because this action essentially breaks some of the gauge invariants of general relativity, but not the spatial diffeomorphism one that we care about in shape dynamics, only the time reparametrization part, because essentially there is a physical degree of freedom that is unlocked by this term. And the potential that the scalar field has is exactly the type that we need for slow roll inflation. And it's exactly the type that we need in order to have quiescence. So this is what is special for me with the scalar field. I don't know if your question regarded whether we can have other types of fields that does this, that gives the dynamics this quiescent property. If that is the question, probably, most likely, but they will not be standard model fields. They cannot be gauge fields nor fermion fields. They will have to, so the only type of field that has been observed in nature that has this property is the scalar one. So again, we go back to observation, essentially. Like we prefer it because of that. I use all these caveats because cosmologists tend to embrace scalar fields quite absent-mindedly. They're like their daily bread, and many people are quite frustrated with that. Like if you look at the amount of papers and works that involve the most fantastic type of scalar field and the analysis of their cosmological consequences is the normal. It's most of the work that is done by theorists. And so people are frustrated about that. I want to say I try not to identify with yet another cosmology studying a scalar field. I'm considering scalar fields for very precise reasons that I think makes it compelling.
Okay, thank you very much.
You're welcome.
Thanks. So I have a question also. So you say that usually in general relativity we look at 4D space-time, and you say that for a certain set of solutions we can use the York method, so to say, and look just at the 3D conformal geometry evolving along with the York time. So can you say a bit more about the set of solutions? So are these all the realistic models of the universe, or do we exclude some models which are important, and So, and if so, if these are the good or the realistic models, then you say we should, well, get away from the 4D description entirely?
Yeah, so it's a very interesting question. Thank you very much. Where is it? Here. If you look at numerical relativity, there's a huge amount of work done in CMC foliation. Because it's very nice to numerics. Okay, because I can, first of all, because I can solve the initial value problem there. I have an elliptic equation and a set of elliptic equations, and therefore it makes it possible to even start evolving my solution. And then they're very nice to numerics because they have this interesting property of being a bit repelled by singularities, apparently, or even by horizons. If you just study the CMC foliations of Schwarzschild spacetime, they collect around the horizon, they cross it, but then they stay like 3/2 Schwarzschild radii, 2/3 Schwarzschild radii away from the singularity. So what regions of space-time, the space-times that we think describe actual physics, do they cover? A lot. Any, if you think about our universe, something that is very close to Friedman Robertson Walker right now, and something that is the region that is outside of the event horizons of black holes, that is all neatly covered by CMC foliation. People do numerics, observe this property of CMC foliations that they bunch around singularities and try to, like if there is a singularity at the center of a certain region that starts here, and the CMC foliation is imaging an horizontal line of equal time, and I evolve it towards the singularity. Away from the singularity, they will continue to evolve smoothly. At the singularity, the equal time lines will bend more and more and more because they try to slow down and not get to the singularity. So it appears that they tend to move the singularities, all the singularities, away at infinite parameter time, if you want. Okay. So this is a curious property. However, we studied precisely a set of a quite varied set of solutions of GR, of singular solutions of GR in CMC foliation ourselves. This is shape dynamics, but it's equivalent to GR only in a CMC foliation. And this is what allowed us to continue through them. So they seem to be an interesting tool to study singularities too, although there is this wisdom that they avoid singularity, because people talk about singularity avoidance property of CMC foliation. So that is not entirely true. What they do is they tend to push singularities at infinite values of the independent parameter that labels your sheets of the foliation. But what we did was to go beyond that and show that they allow you to find a smooth description of the singularity. So I don't know if that answers all the aspects of your question, but yeah.
Yes, thank you.
Lots of back there.
Okay, thank you very much. I think we have to go on to the next talk as it is already time. So thanks again very much for this talk.
Thank you. Should I stop sharing?
Yes, that's.
Yeah, no. Otherwise I will, okay.
Okay.
There we go.
Let's go on to Julian's talk. So,
Hello.
Hello. So now we have a second talk by Julian Barber. So many of you, I think, know him. He's been working on shape dynamics for about 40 years now, which is quite a lot, much longer than I lived. Anyway, so it all started, I think, from a paper from 1982 with from Julian Barber and Bruno Bertotti, where they showed how to formulate physics relationally, and this developed, and he developed this theory with his collaborators until now. And yeah, I'm very happy that you are here today. Maybe let me advertise also your recent book, which was The Janus Point. I think it appeared just last year or this year even. And yeah, so today you talk about the local laws of motion emerging. So thank you.
Okay, well, let's see if I can share screen and it works first.
Let's try.
Share. Is that, well,
it's there, but it's again.
We've got this problem here of
strange.
Of that. We went through this before, didn't we? Well, first of all,
leave it like this now, I think. So just, yeah, we use this. Everybody can see it perfectly, I think.
So what was the trick we did before? We stopped share and then started share again, didn't we?
We did one more time, okay.
And now share screen. Share. That's better.
Great.
Perfectly.
I think that will do, will it?
Yes.
Very much, yeah.
All right, yes, well, thank you very much. And I hope I can push on to the next one. Yes, well, here's some, I think I can skip through that. The various people have been tremendously helpful in all this. And there's Flavio's book, you've seen all that. And there was just a mention of my own. So let's go on to the thing. So in, I can't, can I move? Ah, yes, I can move you out of the way. So there was this famous letter that Isaac Newton wrote to Richard Bentley in 1693, that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum, without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Well, that was was quoted by Maxwell after he'd found the laws of electrodynamics, and suggested, and that was what moved people to say that the laws of nature should be described by partial differential equations expressed locally. And Frank Wilczek, in a recent book called Fundamentals, takes this very seriously. And of course, Frank Wilczek is a great physicist. So I venture to sort of slightly question what he says with some trepidation, but he puts it very nicely. He says, 4 simple yet profound general principles govern how the world works. The basic laws describe change. The basic laws are universal. The basic laws are local. The basic laws are precise. Now, I'm going to put forward an alternative, which is that there is a single master law of the universe, and it describes precisely possible instants of time. Those would be what Flavio was talking about, really, space at a given instant. It describes precisely infinitesimal differences between instants, and it describes the evolution of those instants. And then I will argue that all local laws are emergent manifestations of the master law. And there are certainly increasingly radical possible forms of the master law. They do exist. And the most radical, which I might just get to towards the end, is that the master law describes how the universe goes from maximal possible uniformity to maximal variety. So I start off by
one observation, which I think might be key, which is that spatial relations, not space-time relations, but spatial relations are non-local. So if you take the distances between 5 or more points in 3-dimensional Euclidean space, they satisfy certain algebraic relations. There are much more sophisticated relations in Riemannian geometry, and a compact continuous manifold is, in a very deep sense, a non-local unity. Now, as this has been organized in Germany, I'm going to quote Goethe here. Near the start of his great drama of Faust, Faust is in despair trying to understand the world, and he asks, and I'll quote it in German, "Was im Innersten die Welt zusammenhält," which I'll translate as, what is it in its innermost core that holds the world together? And Galileo said, he that attempts geometry without, natural philosophy without geometry is lost. So I think this is already perhaps reflected in hyperbolic elliptic systems, which are very key in Maxwell. So the initial fields, the magnetic and electric field, must satisfy constraints. The divergence of the magnetic field must vanish. That can be achieved trivially by taking it to be the curl of the vector potential, the 3-dimensional vector potential. Now, the divergence of the electric field must be essentially equal to the charge density, or it vanishes if there's no charges. And if these elliptic Maxwell equations are not satisfied, it's not possible to use the hyperbolic evolution equations. And importantly, if the constraints hold initially, the evolution equations ensure that they continue to hold. These constraints are timeless and hold at any instant across arbitrary spatial distances. My friend Karol Kuchasz, who did a lot of work in quantum gravity, described them as laws of the instant. I find that expression very suggestive, and I wonder to what extent it's compatible with what Newton said and Maxwell so admired. Of course, there's no wave propagation in an instant, but nevertheless, there's a very tight interconnection that holds right across space at any instant. And there are much more complicated constraints held in general relativity. Flavio was talking about them in his previous, in his talk. There's one of them. So first of all, there are 3 linear constraints, which are just like the Gauss constraint. But then there's on top of them, there's a quadratic Hamiltonian constraint, which suggests that the quantum universe is static, and that's given rise to this day unsolved problem of what's called the problem of time. And that quadratic Hamiltonian constraint is coupled to the linear constraint and constraints, and that's really why they were very difficult to solve. And that's really what this very significant achievement of Jimmy York and Nila Murukku in finding a way to solve it, which is mathematically extremely robust. They arrive at an equation by the technique called the Lishnerovich-York equation, and what Neil in his PhD proved was that solution that equation has a unique solution, and it's very striking. So there's some very, very solid mathematics that underlies that. So I have been criticized by someone I regard highly for talking too much, expressing the ideas of shape dynamics with Newtonian particle dynamics. But I think this is missing the point, and I want to emphasize it here. Underlying this is, well, there is a huge difference between particles in space and field theory, but it's a question of architectonic structure, and it's really the role of group theory in the dynamics of the universe that counts. So if we have, I've already mentioned this for n equals 5. So if you have n points, there are n into n minus 1 divided by 2 algebraic relations between those n points in Euclidean space. And they allow representation by 3n Cartesian coordinates. So that's massive data compression, essentially from n squared to 3n, but you're left with 6 gauge degrees of freedom. You can rotate the complete configuration of those points and translate them. And there's a similar and much greater redundancy in dynamical geometry. So there are group theoretical issues which come in very fundamentally. And I would say they are essentially common to both particle dynamics and dynamical geometry. It's just the difference between a symmetry group that depends on a finite number of parameters and a symmetry group that depends upon arbitrary functions. Now, of course, the latter is much more complicated, but nevertheless, it's group theoretical ideas that are underlining it. In many ways, Leibniz anticipated group theory when he pointed out in a famous debate with Clarke, who was representing Newton, that translations and rotations of a complete collection of points is meaningless because nothing could be observed within the system. If you're within the system, you can't identify, you can't see any change. And he says that to think that translating and moving the whole universe, rotating it, moving it, changes anything is just ridiculous. And he says that's against what he calls his identity, his principle of the identity of indiscernibles. Now, another thing which is very interesting, which Poincaré pointed out, and for me, it's exactly what is really the problem that comes from Newton's use of absolute space. Poincaré said he was firmly convinced that motion is relative. And he said, suppose at some instant I know the relative positions of the particles, what are the separations between the particles, and suppose I also know how those separations are changing, the rate of change of those separations. Now, if I believe in relativity of motion, that should be enough for me to be able to predict the future uniquely. And he pointed out that that is just not the case in Newtonian dynamics, because that information, the current configuration and the rate of change of the configuration says nothing about the angular momentum in the system. And if there's angular momentum in the system with different magnitudes, you get completely different evolution from what looks like identical initial data. And there's why, so this goes against Leibniz's principle of sufficient reason. You cannot find why there should be one evolution rather than another when the initial condition seems to be identical. And another issue is going to be size. Poincaré also emphasized that if you change all the sizes of the universe, you can't observe anything. It all looks to be quite the same. And at the moment, now I've forgotten what the other 2 points I've put down here about nature and direction, but we'll no doubt come to that later on. So I just want to say how the problem that Poincaré identified is resolved by the technique that Bertotti and I developed, which when we did that in 1982, we called it the intrinsic derivative, but I since changed it to the idea of best matching. So Flavio complained that in the last talk I gave, I didn't show my beloved triangles. So here they are, Flavio. Let me first of all quote what Mach said on these things. He said, the universe is given once only with its relative motions alone determinable. Now suppose these two triangles represent that there's going to be 3-point particles. They can have different masses, and they're always going to be at one of the vertices of the triangle. So in the picture on the left, which was taken on my kitchen table, and that bit of white paper is meant to be absolute space. Those would be two possible configurations of the particles at different times. And those triangles are incongruent. They're not the same shape and they're not the same size. And this is really what gives rise to the problem that Poincaré didn't like, that the future is unpredictable, because where you put those triangles relative to each other, you are actually rotating one relative to the other. The displacement doesn't matter because of Galilean invariance, but rotating one relative to the other changes the angular momentum and completely changes the evolution. But there is one way, and this is where so first of all, that's the problem. The first thing that comes in through group theory, the identity of indiscernibles. You can imagine rotating either of the triangles on the left relative to the other. And as regards their position in absolute space, nothing is observable. However, what you can do is imagine that you try and bring them, you can't bring them to exact congruence because they're incongruent, but you can try and bring them as close as you can to congruence. And that involves bringing the centers of mass to coincidence and then trying to minimize. So you've got a particle at each vertex, so the two common vertices. So look at the two vertices on the left in where I'm trying to bring them to congruence. There's a distance there. So that's particle 1. And we'll say the distance between that there in that position is dx. And I multiply it. Sorry, yes, it should be squared. So I'm going to square that distance and multiply it by the mass. And I'm going to do that at each of the 3 vertices. And then I'm going to take the square root of it. And then I've got something which is a little metric distance. And that quantity is positive definite. So the resulting, so then I can rotate and move the one triangle relative to the other until that quantity is minimized. And there is a unique minimum. And so I call that result the best matched distance. And it's background independent. Background independence is a great issue in quantum gravity, particularly in canonical quantum gravity. So this is one way of achieving background independence. It doesn't matter where you move those two triangles on the right. Once they're locked into that best match position, you can move them wherever you like on this piece of paper or all over my kitchen, and nothing will change the value of that best match distance. And in that case, I would say that the blue triangle has been horizontally stacked relative to the green triangle. So I now recall Jacobi's principle and the emergence of time. So in Jacobi's principle, how it's normally presented, if you have a system with a given energy E, and here I'm going to take it that the energy is 0, but if the energy is, you have one value of the energy, you can describe the evolution as a geodesic in the configuration space of the system. And that gets rid of time. So now this is the form, the top equation here is the form that Jacobi's principle takes if the energy is zero. So here is, it would be normally a capital E there minus the potential. So the Newton potential is negative. So that is there what the role of the Newton potential. There's no energy there. And this is what the kinetic term looks like. However, lambda is an arbitrary monotonic parameter. So this is reparametrization invariant. It does not, you can change the lambda, and as long as it's done continuously, you don't change the value of the action. So the action is reparametrization invariant. So as I said, you can have an energy going in there as well as the potential, but any value of the energy that is not zero is again, you have to say, well, what could fix that value of the energy? It's against Leibniz's principle of the sufficient reason. So taking the energy zero, which also non-zero values of the energy actually reflect the fact that the absolute time or the independent variable time allows you to have different initial velocities when the particles are moving in certain directions. So here's the equation of motion that you get from the Euler-Lagrange equations, and it looks pretty unpleasant with all these factors of v over t or t over v. But the lambda is completely free. So you can choose lambda in a special way, and then you denote it as t, and you choose it such that t is equal to minus v. And you can always do that. And in that case, your equation reduces to Newton's second law with zero energy. So that's how you can implement Mach's requirement. I think I've got the quotation on the next thing. Yes, here's on the next page here. It's utterly impossible to measure the changes of things by time. Quite the contrary, time is an abstraction at which we arrive by means of the changes of things. Now, I'd like to make a distinction between time, or rather instants of time, and because Isaac Newton, I think very helpfully spoke of absolute time, but he said that by another name, it's called duration. So I met that model on the left, I made it about 40 years ago when I was doing this work with Mercati to illustrate what we called horizontal and vertical stacking. So horizontal stacking was when we so we start with the triangle in the bottom position there, and then horizontally we move the next one into the best matched position relative to that one. But then we do that all the way up successively, and we've made something like a pack of cards. But then we put a vertical separation between the various cards, or the instance of time, to represent this special time variable that I chose. And I think, and Flavio's diagram is on the right there, where it's shown a bit more professionally. But I like the one on the left because of it's very material with those bits of cardboard, because I think there's nothing wrong with having a childlike impression of the world. The world is full of things you can touch and see, like my fingers and hands. You can see that there, and I like the way you can see those cardboard triangles, and I would say that they are real things, but the gaps between them, the vertical gaps between them, that's just the way we've arranged them to make the change as you go from one bit of cardboard to the next look as if it's happening in accordance with laws of motion in a particularly simple way. So that is really very emergent. And Flavio was saying about this work that Jimmy York and Neil did with finding the solutions to the initial value constraints in general relativity. Well, that is just actually best matching writ hugely large, because the best matching in that case involves the infinite dimensional. I think this may be on the next slide. No, sorry, I've already put that one there. Let me go back again. In general relativity, you've got best matching with respect to the three-dimensional diffeomorphism group and the three-dimensional conformal group. So they're each dependent upon a great number of arbitrary functions, but the underlying principle is exactly the same. And in that way, you get not only at each space point, you get the difference of proper time as you go upwards, forward in time, if you like, forward with the evolution, but you also get the metric distance in space between points. That's all filled in by solution by this best matching thing. And in fact, you could have got at general relativity could have been derived in a completely different way, which had been suggested by Clifford, who translated Riemann's paper of 1854, when he suggested that geometry could be dynamical. So if he had got together with Mach, they might have come up with vacuum general relativity without any intervention, without any preparatory stuff being done by Minkowski with the creation of Minkowski space. So that's why I think it may be the case that particle models give us some useful hint about what the world really might be like and what's going on. So anyway, I've shown that one. Oh, I will just mention that this is how local inertial frames of reference can emerge. So if we just have three particles, that's where they are. They move in accordance with Newton's law in the inertial frame of reference that just the three particles create for themselves. But in a universe where there's a huge number of particles quite a long way and just three particles that have more or less self-isolated themselves, it's the distant particles that predominantly create the local inertial frame of reference. So the universe at large is having a colossal local effect, and you feel that whenever there's a train crash or a car crash, what's happening there. So I'll go through this rather briefly. There is something called the byline Sharp-Wheeler action for general relativity. In the first equation, I repeat there what the Jacobi's principle for particle dynamics is. And the byline Sharp-Wheeler takes this form here, and you can use it when you've got, Flavio was talking about CMC foliation. This is basically very much the same, and I've already talked about that it's best matched to be in constant mean curvature foliation. And so instead of the Minkowski-Einstein block universe with space as the order, it replaced that with space as the order of coexisting things and time as succession of coexisting things, which is what Leibniz was saying back over 200, 300, is it? 17, 15, 16 years ago, 300 years ago. So space-time that is locally Minkowski is emergent, and the sort of spars that there's padding that holds out that you can put in between points in space, and then there are props which hold up time, and it's all wonderfully local, but the whole of space-time is emergent there. Now I come on to what I think is really possibly could be the key to quantum gravity, which is trying to understand time or scale or both together. Let me just look at the extent to which the these two variational principles are scale invariant. Well, they're not. They're nearly, but not quite, because the kinetic term is quadratic. So that's length, its dimension is length squared, and the Newton potential is homogeneous of degree -1. So there's the length to the -1 there. So the overall dimension of the action is the square root of a length. And it's exactly the same in the Bioline-Sharp-Wheeler action. So the scale non-invariance of the action in both the n-body problem and in general relativity, it's what allows you to say there's an initial size in the system which is nominal, but at some other epoch, there's a doubling. There can be, it will be some fraction of that initial size. And I'm going to show you how this failure to be scale invariant is what leads to all of interesting structure formation, I believe, certainly in the n-body problem, and I believe in the whole universe. Now, you can have a geodesic principle, but to do that, you have to have a potential which is homogeneous of degree -2. But if you have that, that's a maximally predictive law. You might think that that is the ideal law, but in fact, it doesn't lead to anything interesting. I think I'll just have to ask you to take my word for that, but we'll perhaps see why. Now, I want to come on to what I think is certainly in the n-body problem, and I think there's something analogous. I conjecture that there's something analogous to it in general relativity. So in the n-body problem, it's called the Lagrange-Jacobi relation. So now the center of mass moment of inertia, there's the expression for it there. And it's essentially the mass times the square of the root mean square length. There's the expression for the root mean square length. You take all the separations between the particles, square them, multiply by mass pairs, add them up, and take the square root. Now, there's a relation which is trivial to prove, and Lagrange already did it in the three-body problem in 1772. If the potential is homogeneous of degree k, then the second derivative of the center of mass moment of inertia is has this form here. Now, and where that's the potential, and that's the degree of homogeneity. And here's the Lagrange-Jacobi relation, which in the case of the Newton potential, because the Newton potential's got a -1 there, that means that this comes down to be 2, and there's still the minus there, but the Newton potential is negative definite. So if the energy is non-negative, because the Newton potential is negative definite, the second derivative of the moment of inertia is positive definite, and this means that as a function of time, the moment of inertia is concave upwards. So this is what you get here. So this is the situation when when the energy when the size doesn't go to 0 and the energy, this is a weak condition, the energy is non-negative. So the size is infinitely great in the past. It comes down to a finite value, which is what I call the Janus point, and then it again grows to plus infinity. And I'm going to show you that not only does the size increase, which is a gauge degree of freedom in shape dynamics, you can't see it, but the universe is most uniform around here, and it clusters in both directions, and that defines arrows of time, bidirectional arrows of time. Now, there are special ones. Flavio mentioned this, the total explosions, total collisions in the normal way, when the system, all the particles collide at once at their center of mass. Now, by time reversal, you can make that into a Newtonian Big Bang. And the existence of these things has been known for about 130 years, discovered before the expansion of the universe in general relativity. These are zero measure solutions, and they need the angular momentum to be 0. And you have a unidirectional arrow. It's profoundly time asymmetric. And these distinguished points, the Janus point there or this point here, they are a direct consequence of the law. They're nothing whatever to do with a past hypothesis. So now I'm going to introduce, this is where group theory comes in a third time. I'm going to introduce something which we call the scale invariant complexity. So this quantity, its original idea for it was to measure the extent to which a distribution of particles is either uniformly distributed or clustered. So it's got to be scale invariant. And so you consider the root mean square length, that's got the dimensions of length. And then there's the mean harmonic length, which is actually the inverse of the Newton potential. So if you take so there are the explicit expressions for them. If you take the ratio of those two quantities, you get what we call the shape complexity, the ratio of the root mean square length divided by the mean harmonic length. And this is a very sensitive measure of clustering, because if two particles get close to each other or even collide, that has and there's a lot of particles, that has very little effect on the root mean square length. But if they actually collide, this thing will go to infinity and the complexity becomes infinitely large. So it's a very sensitive measure of clustering. Now, Flavio was showing a shape space for in Bianchi IX, but there's a shape space in the three-body problem. So each point on the surface of the sphere represents a shape of a triangle, not the size, just the shape. And here are the contours of the complexity. And it rises. This is where two particles get relatively much closer to each other than the third one, and it goes up to an infinite peak. This is for equal masses. There is the absolute minimum is at the equilateral triangle, and then there are saddle points on the equator of the collinear configurations there. So the complexity is a pure number, and this is a sort of guiding principle of shape dynamics, that everything must be expressed in terms of ratios of quantities of the same kind, and it's an invariant of the similarity group. So that's the third use of gauge theory coming in there. So this complexity, this is, so to speak, what you can see. So this is from a 1,000-body numerical simulation from the paper of myself, Tim, and Flavio back in 2014. Jerome Barclay kindly did these numerical calculations for 1,000 bodies. If you have the three-body problem, there are big fluctuations in the complexity, but it rises between linearly rising bounds. And for 1,000 particles, it more or less evens out. So you get this pretty impressive linear increase of the things. And there is an argument, it's a heuristic argument. I won't repeat it here. I did give it in a talk I gave on a golden webinar, which I think is going to be posted at some stage soon. But basically, the situation you have is at the Janus point, it's like a swarm of bees. It's very uniform, and basically it's going to have a thermal distribution of particles typically. I think there are quite strong statistical arguments for that. And then as you go away in both directions from the Janus point, clusters form, particles systems self-isolate themselves. So so now I wonder, I mean, a huge thing ever since, well, thermodynamics was discovered, and particularly in the 1890s with the famous debate between Boltzmann and Zermelo, there's been a huge issue about where does the entropic arrow of time come from? Where does the arrow of time come from? And the consensus to this day is that there must have been some very special event state in the distant past. But in fact, if you just look at the Newtonian n-body problem, and you look at every possible solution, they virtually all have an arrow of time, except for, well, first of all, there are some negative energy solutions. They remain permanently bound, and they do behave thermodynamically. If they're permanently bound, they have virialized and they satisfy the Poincaré recurrence, and there's no arrow of time in those solutions. However, most negative energy solutions, so this is the great bulk of the negative energy solutions, are unstable, and they exhibit bidirectional arrows of time, just like the ones we were looking at in the previous slide, either side of a Janus region. And then all the solutions with non-negative energy exhibit those bidirectional arrows of time. And then there are, I mentioned, these time asymmetric Big Bang solutions. Now, all of these solutions I've talked about in statistical mechanical terms, they are microhistories. And the arrows of time exist in the microhistories. It's nothing whatever to do with a statistical effect where you're looking at a Gibbs ensemble of solutions and you see the sort of the entropic behavior in such a thing. So this is just a complete counterexample. Wait a minute. I'm doing things. Yes, so let's think about this. I would say that thermodynamics and statistical mechanics are emergent. Now, Gibbs, if you read Gibbs's book on statistical mechanics near the end of his life, he says he has to consider dynamical systems with phase spaces of bounded Liouville measure. Well, he doesn't say that explicitly, but that's what he's requiring, because he needs to talk about probabilities. And this corresponds actually to the discovery of thermodynamics by Carnot, essentially by studying a steam engine, where the steam has to remain in the cylinder in a box. And all of statistical mechanics was developed for systems in a box. And Gibbs bases the whole of statistical mechanics on Liouville's theorem, and that leads to the thermodynamic behavior of Gibbs ensembles. And I've already mentioned, I mentioned Boltzmann's difficulties in the debate with Zermelo, but it was Poincaré recurrence that thwarted Boltzmann's attempt at a dynamical explanation of the second law and the entropic arrow of time. Now, I'm going to suggest that really for the universe, we have to go from Gibbs to say it's not Liouville's theorem, but it's the Lagrange-Jacobi relation. I've put that in scare quotes because, well, in many ways, Newtonian gravity is a very good description of what is happening in the universe. And I suspect that that's what you need, something like that. And there will be something like that in general relativity, which then to a very large degree will coincide with the Lagrange-Jacobi relation that you have in the n-body problem. And this will be what you need in an unbounded phase space. And I've already made this point. If the energy is non-negative, the complexity of the universe must increase. There's no past hypothesis. But that defines the increase of the complexity, which we saw in the earlier slide. That defines a gradient. You go up there. So what about the entropic gradient? Does that align with the complexity one that I was talking about? Well, if you go back to that, let me go back to that picture here. So this is the artistic impression that Flavio created. So as you go out here, as that complexity is increasing, the increasing complexity means that these subsystems are forming. As they form, they start with a low entropy, and they virialize transiently, and then they decay. And there are no permanent systems in the universe. Even black holes decay, according to Hawking's result. So you get this transient formation of isolated subsystems, which begin with a low entropy, increases, and then they decay. And that arrow of time, the entropic arrow of time, agrees in the same direction with the complexity one. So I see here a chance to unify thermodynamics and these ideas here. I'll just make one point here. I think Hamiltonian dynamics is emergent. In a Machian universe, the momenta are constrained. So the energy and the angular momentum must be exactly zero. Well, you can also have the total momentum if you're in the center of mass frame. And that is constrained Hamiltonian dynamics. This is a particle model realization of those incredibly difficult constraints in general relativity, in the initial value problem of general relativity, that Jimmy York and Nilo Moroku found the way to find the solutions to it. Now, as you get subsystems self-isolating, these ones here, they conserve ever better energy, momentum, and angular momentum. Each of them are doing that. And they're all sort of correlated with each other in a remarkable way. So you actually get emergent Hamiltonian dynamics. So the whole universe always is described by constrained Hamiltonian dynamics, but subsystems form, and they are described by emergent Hamiltonian dynamics. Now, quantum mechanics really seems to have consisted in just, if I get this right from memory, you start off with the ordinary canonical variables in Hamiltonian dynamics, and you make them anti-commute. So this makes me suggest, if Hamiltonian dynamics is emergent, is Hilbert space quantum mechanics also emergent? Well, I'm getting quite near the end of it there. I mentioned this fact that the action principle for particle mechanics and for general relativity is not scale invariant. Now, there's something very, very suspicious about that, because how do we actually measure any lengths? We measure things within the universe. So how large is the universe? Well, let's say that the Hubble radius defines the size of the universe. Well, it's a certain many times greater than the length of my body. It's a ratio of something within the universe. And yet it's very strange in the action principle for both ordinary Newtonian dynamics and general relativity. When you're using the principle of least action, you have to specify, what you do is you specify a size at each, or a volume at each limit of integration. And then you say that one of them is nominal, and it's only the ratio that counts. But that's why you can say that the universe today is twice as large as it was whenever it was so many billion years ago. And that's rather strange, because if you look at these remarkable things, now these are these remarkable central configurations that Flavio mentioned. This is the shape. These are done in 2 dimensions, but they're basically the same as what's happened in 3 dimensions. The universe must have a shape like this if it's going to have a total collision or a total explosion. So this is actually, if you say that the volume or the size of the universe is gauge, this is actually what the shape of the universe looks like at the Big Bang, if this is a reasonable model of it. And it's extraordinarily well behaved. Look how well behaved it is there. So this configuration here, this shape here, corresponds, is very close to the absolute minimum of the complexity. You only increase the complexity by really a very relatively small amount, and you get this incredible pattern of particles here, voids and filaments. And this extraordinary structure was only discovered quite recently through numerical calculations by Manuel Izquierdo. Hints of these voids and filaments had been found earlier, but not in this remarkable thing there. So how big are these universes? Well, you measure the universe by the shortest distances. So this could be my body here, and there's the size of the universe. Well, it's whatever it is, 40 times the size of my body in this particular case here. So I'm extremely suspicious about the role of scale in cosmology and in general relativity. And so I have conjectured, and I talked about this in the shape dynamics one we had recently, and it's also in my golden webinar talk. Could it be that complexity is time and size all in one? Well, I think I better stop there. Yes, that is my last slide. So let's go over to questions from there. Thank you very much.
Okay, thank you, Julian, for this very interesting talk. So please let us open this up for questions. Okay, so there's the applause, and there's already the first question. Okay, so Eric Ling, you can ask.
Okay, great. Thank you for the really nice talks, Julian and Flavio. So this question is just in regards to, we observe these FLRW models that describe the large scale structure, and Flavio was talking a lot about homogeneous models. So what work has there been done just on the, the more simpler isotropic cases?
Sorry, was the question for me? Because I'm afraid I didn't quite catch it. If you could say it again, if it was for me.
Right, it's for either both you or Flavio, maybe more for Flavio since he was working on it.
More for Flavio, okay, fine.
Yeah, maybe more for Flavio. It's just, you have these, you're doing shape space on anisotropic homogeneous cosmological models, right? Yeah. But I think before doing that, one should ask, one should do shape space on just the isotropic case, right? And I guess, you said that when X and Y were 0, then you get back the isotropic S3, right? But what about just like the, Euclidean FLRW or the hyperbolic one, right?
Yeah, that's a good question. So thank you. If you a solution of the Bianchi IX system, which of course is a system that is rather complicated compared to FRW. It's a midi superspace answer, not a mini superspace one. There's one solution of a more complicated system, that is the representative point sitting at the origin and having 0 shape momentum. So it just sits there. What is that? That is FRW, because the universe is always isotropic. So at least for a spherical, so for closed FRW cosmologies, you get that. However, this is really at the core of the issue of what is physical and what's not. For shape dynamics, that is not an acceptable solution because nothing happens.
Yeah.
It's stuck at the center of shape space and the shape never changes. So anything that you can measure as the rate of change of one shape degree of freedom with respect to the other will be 0, and nothing will be changing.
So then, so just as a question, like physically, ideally, what you would want then is you would want that shape to not necessarily be changing the closer you get back to the Big Bang, right? But then after the Big Bang, then you want the shape and the structure to emerge from that, right? So in some sense, large scale, you should still have some FLRW, but then on the smaller scales,
Absolutely.
this is when you'll see
but this is exactly what you observe. So the solution that sits on FRW and does nothing, all the evolution is in the volume and therefore is unobservable. So it's a sort of artifact for shape dynamics. But this doesn't mean that usual cosmology, which is the perturbations around FRW and matter fields on FRW, is invalid. It's actually a perfectly valid model that is full of physical content. Why? Because you're not considering only the dynamics of the volume by its own. You're adding many degrees of freedom, and you're considering what happens when the solution is a small perturbation around FRW1. Now, in Bianchi IX and in general, there's good reason to believe that for general solution, anisotropic ones with many infinite degrees of freedom that are genuinely physical and local, one gets that at late times, so away from the Big Bang, you remember I showed that the shape potential is multiplied by some power of the volume. Therefore, it's less important as the volume goes to zero. And as the volume goes to zero, I explore larger and larger regions of shape space. Okay, so more and more anisotropic background universes. Well, if I explore the opposite direction, so as I go away from the singularity, the region of shape space that I'm allowed to study, that my representative point explores, is smaller and smaller around the origin. Therefore, the universe tends to be more and more isotropic as I go away from the singularity. And this is even so in a general, in a free Bianchi IX solution, this has a limit because at some point I reach the big bounce. I stop increasing my volume and I start compressing again, and I go towards the new Big Bang. But if I add a cosmological constant or any matter that causes any sources that cause expansion, I have a big region of this space, which if I enter it, I will go into runaway solutions which expand forever. And that's, for example, what happens with inflation. The scalar field causes, this 60-fold expansion of my universe. And as the volume expands very fast, my anisotropic parameters are constrained to become smaller and smaller. So I approach a more and more isotropic universe. That's why FRW is a good description at late times. Okay. I went through the whole sketch of a proof very quickly, but the message is the generic dynamics of anisotropic universes near the singularity tells me that I will tend to evolve towards a universe that is very well approximated by isotropic FRW at late times after inflation and after all of standard cosmology takes place.
I didn't quite get that. Did you say it should be isotropic at late times or at early times?
It gets anisotropic at early times and it gets more isotropic at late times towards our epoch. Okay. So towards the Big Bang, I get large anisotropy. Here we're talking about pre-inflationary dynamics, so something that we have little experimental data on, or no. But the dynamics of Bianchi IX speaks clearly. I have huge anisotropies towards the Big Bang, and I have a tendency to evolve towards isotropic universes away from the Big Bang.
But okay, I just have a problem with this because this is not, I mean, based on readings of Roger Penrose and stuff, I mean, regardless of inflation, just typically what we observe, know, when you go back in time and you have the, this, the, recombination era and stuff like that, things are more isotropic when you go towards the past, and things become less isotropic as you go forward.
Are you confusing inhomogeneities with anisotropies, for instance? You were talking about large-scale anisotropies. So the whole universe, as if you could fly in a space-like curve in one direction, you would end up coming back at the original point. If you do that in different directions, it takes different times. That's an anisotropic universe. So it's nothing to do with the normal development of homogeneities, which is a consequence of gravitational dynamics. These are large-scale anisotropies. And as far as we know, the universe is immensely isotropic. It's very small, the anisotropic properties at large scale from what we observe. Okay.
I guess maybe I'm just not understanding correctly. I do on large scales, the universe is isotropic, but in just the standard, or not thinking of Bianchi or the anisotropic homogeneous, but just thinking of the normal isotropic, and then using that to model our universe, right? Part of Penrose's motivation for introducing the wild curvature hypothesis was that you would think that isotropy should be you should be more isotropic as you get closer to the Big Bang and less afterwards, right? When you're close to the Big Bang, you have a bunch of particles, right? And then eventually those particles will come together and form, stellar objects, galaxies, and black holes, and that's causing anisotropy.
No, that's
right.
Inhomogeneity, not anisotropy. It's causing a lot of inhomogeneity. Yeah, anisotropy is a different matter altogether. The universe, the model you're talking about is a perturbation around FRW, which is by definition isotropic at all times, isotropic and homogeneous. But then you study little perturbations around it only in the inhomogeneity degrees of freedom. So gravitational dynamics tends to clump galaxies, clusters, etc., and cause inhomogeneity. And anisotropy would mean that on the left side of the universe, there's a lot more space somehow. No? It's much, the universe is much longer in that direction than in this direction. That's a different degree of freedom, essentially. Okay.
Okay, so maybe you have another question, or we go on with the next question. So Dirk, you can go on.
Yeah, I would maybe even have two questions. Maybe one for Julian first. This nice picture that you showed in the last slide. Could you give a couple of details how it is really generated? So, of course, I would be interested in where these structures emerge from. So on the left-hand side, for example, I see there might be some initial positions which are not completely symmetric. I don't know, do the points all have the same masses or different masses there? And the dynamics, I guess, are the same that you showed in the very first couple of slides, right?
Yeah. Now, first of all, there's no dynamics in this. These are configurations that are extrema of the complexity. And they're called central configurations in n-body theory. And if there's to be a total collision, the shape must tend to one of these. The shape of the n-body system, the particles must tend to shapes like this. I mean, these are very remarkable things. So these ones were calculated for 1,000 equal mass particles. But if you have a mixture of masses, if the range of masses is not too great, they basically come out looking much the same. Now these shapes these central configurations are very remarkable. There's an incredible number of them. The number is essentially, if n is the number of particles, the number of these central configurations is n factorial. Mm-hmm. And I mean, I mentioned in my talk that Maxwell didn't like the idea of action at a distance, but he created his theory with wave propagation, but he introduced constraints. So those constraints hold across all of space. So the momenta, they constrain the momenta. The momenta cannot be freely specified. And in general relativity, the restrictions are very severe at each space point. They're not just a vanishing angular momentum of the whole universe, they're at each space point. Now, what is very remarkable in these total collisions or total explosions, it's not only the momenta that are constrained, it's the positions are constrained. So this is a very remarkable state of affairs. And I mean, we got into this actually because of a challenge from Pedro Ferreira to see if we could find an alternative to inflation within n-body theory. And bit by bit, mainly because I've been interacting and having discussions with n-body specialists for many years, we realized how extraordinarily uniform the initial shape of these total explosions are. I mean, just look at it. It's very, I mean, that's what the one on the left, that's what it's like. And that's, as I say, that's a constraint on the positions and not just, it's a constraint on the shape. So this is, I think people should contemplate what that is. And I mean, I would say shape dynamics will really be a success if we can actually show that inflation is not the correct theory of the universe, that it actually, it's this big, am I sharing this? I'm sharing the screen.
Yes, yes.
Yeah, if that's what the universe starts at. Now, interestingly, these central configurations, that shape, if it's the absolute minimum, and it might well be of the complexity, it's the most uniform shape that the universe can have, but it's not absolutely uniform. It's not, you don't get to sort of lattice type perfect things there. So in this picture, I mean, the great issue in inflation is you somehow or other we're supposed to believe that the universe gets into a de Sitter phase. It's expanding, which is completely uniform. And then the fluctuations of the inflaton field is what bring in the fluctuations, which then enable systems bound, I mean, clustering to happen and structure to form. And that's what inflation is meant to do. Well, you get these total explosion solutions, just reverse these total collision solutions in general relativity. They start off incredibly uniform, but not perfectly uniform, and then structure grows. And that's actually a higher value. That's also a possible one, but this is the sort of thing that I would envisage. So this is potentially a replacement for inflation, and it's sitting there in Newtonian theory. This is nothing to do with fine tuning. There's no struggling to tweak the inflaton or anything like that. That is just what Newtonian theory tells you. If you want to model general relativity, if you want to say, does Newtonian theory, which is known to be a good approximation to general relativity, give us any hint of what might the Big Bang might be like? Well, if Newtonian theory is a good guide, it looks like that. That's what it looks like. And I think that is pause for thought. And it's an interesting fact that I don't think anybody working in virtually nobody who works in cosmology knows anything about these total collisions and total explosions. It's completely unknown in the field.
Yeah, I also appreciate that. But more technical also the question, I mean, so you somehow compute these things by a minimization process.
I mean, the man who did this, Manuel Izquierdo, he's now actually in the Mallorca. He's working numerical work with neutron star mergers, but he had 3 or 4 months in Paris with the n-body specialists there. And he got into this very quickly. He has a I mean, I'm not at all good on numerical methods, but his supervisor, Alan Albury, was very impressed with how quickly he got into it. And he's got one of these very powerful techniques for finding extrema. He starts with some random thing and then he works these things. I think these 1,000 particle ones take him a sort of a couple of hours to create them there. But there's very interesting things about it. I mean, one thing that I had predicted before these calculations were made on statistical grounds, that all of the smallest separations would be more or less the same. So if you look, the smallest separations, well, it's very interesting. The smallest separations when you're away from these filaments are more or less the same. But when you get into the filaments, they're closer together. Well, I mean, this is maybe way over the top to suggest this, but we know that in gravity, measuring rods must be shorter, so to speak, closer to the sun. So when measuring rods are close to other matter, they get shorter. Is this some hint of this? I mean, and by the way, Alan Albury, who was the supervisor for this work, who's one of the world's leading experts on these remarkable central configurations, as of now, there's no satisfactory explanation for why these remarkable filaments and voids appear. And they're not totally unlike what the universe looks like at the moment. You know, the galaxies strung out on filaments and voids.
Yes, yeah. But I mean, how does the right one relate to the left one? The right one is just a different.
It's just a marginally higher complexity.
But
minimum.
Pardon?
Another local minimum of the complexity function, I think.
The one on the left is either it's a local, it's certainly a local minimum on the left, and it might just be the absolute minimum. But there are, as I say, it's n factorial, so it's 1,000 factorial of these things exist at least.
I see. Okay, thank you very much. Now, Paula, I don't know if I have time to put my second question, or someone else wants to ask something before.
Oh, but go ahead. I think it's time enough.
Okay. My second question was to Flavio. Is there any, I mean, in the systems that you have studied and where I thought I understood that you claim to continue the dynamics through the singularity, how should we think of this continuation in physical terms? I mean, what is this property somehow? What kind of state goes through the singularity, and what kind of state comes out of it? Is there something like a scattering through the singularity, or do we know anything about these properties? I mean, what goes in, what goes out? Is there anything you can say about that?
Yeah, thank you. It's a good question, and the honest answer is we don't know much yet. What we know is that it seems that the orientation of space flips through the singularity. We don't know whether this is something that is actually observable in the sense, whether that is something that is physically meaningful, because in this universe we have stuff like the parity violation in quantum field theory that you can test with particle decays, and gives you a preferred orientation for space. And it's really a relationship between the orientation of space and orientation built in gauge theories and quantum field theory that counts. By studying gauge fields and their continuation through, we will be able, for example, to tell whether in the other universe that is on the other side, an experimental parity violation will give the opposite answer or not. That's one little thing, but there's a lot to be done. There's a recent paper by Ashketer on continuing through the Big Bang, the state of the quantum field theory. They have a recipe for mapping the state of the quantum field before and after the Big Bang, and they're assuming that they're not studying really the gravitational dynamics at all. They're just gluing together two singular spacetimes. Presumably, there's a close relation with what we did, and they seem to be able to define a rule that is deterministic to map the state of the relativity, but a quantum state before and after, which is very interesting. We know that the dynamics that we studied gives a lot of importance to, as I said before, anisotropies, and there's a very dramatic evolution in the phase that goes between inflation and the Big Bang, so beyond the inflationary era for us, so something that is very hard to connect to our cosmological observations at the moment. During this epoch, there is this what Misner called mixed master dynamics, because he really thought that the dynamics was so chaotic that you erase information in a really irreplaceable way, in a really fundamental way. So whatever state, we know that it's chaotic dynamics, and two very closely related states, two initial states that resemble each other very much, will evolve into two very different states after a chaotic dynamic. And so there's not so much what goes at the singularity, which we have quiescence, that's very much deterministic and predictable. But there is this sort of screen of chaos in between the Big Bang itself and the inflationary era that erases a lot of information. On the other hand, a chaotic dynamics has interesting ergodic-like properties. There is a recent paper, 2019, by Stone and Lake on the three-body problem, which actually does essentially, I really like that paper because it essentially studies the statistical shape dynamics of the three-body problem. Okay, that is the n-body Newtonian dynamics, but it has this property of chaos, because if there are at least three particles, there are regions of each solution which evolve towards, if you want, integrable solutions in which everything can be predicted, because you have Kepler pairs evolving in one direction and a singleton being expelled in the opposite direction. But in the middle, between these asymptotic states, there is a region where there is a complicated three-body dynamics that is chaotic. So two very similar solutions will evolve through it into very different solutions. But because it's chaotic, they exploit that in order to define an ensemble and do statistical predictions. So they can give you the probability distribution of different orbital elements for the final state that goes through that chaotic evolution. Why can't we do something like that with the fully general relativistic dynamics that evolves through a Big Bang in a mixed master like epoch? Probably we can say something like, I don't know, certain properties of your cosmological solution will be more probable than others. This sort of statistical statement that makes sense when you have a dynamic that explore a large portion of your phase space, like the chaotic dynamic of the mixed master model. So, but really I can't make statements of this sort at the moment, but I think this is the way.
So very naively, can I compare it to, I mean, I can flip a coin and in principle it's theoretically possible to compute the trajectory, but in the end only statistics will be useful to predict what the outcome is. Yeah. Would that be similar for traversing one of the singularities, that since there's this chaotic dynamics in between, more or less we will in the end probably end up by saying what are the probabilities to end up in one scattering solution or the other?
Yes.
I see. Okay.
I think that's the case.
All right. Thank you very much.
You're welcome.
Okay. So thanks. I think this is a good point to thank again both of the speakers. And yeah, thanks for coming. And I think this is a good point to end this discussion round. And maybe Dirk, you can say something about the next event.
Yeah, I only want to say a few words. So also for me, and from also behalf of all the organizers, thank you very much for these beautiful talks that you provided us. Gave us a lot to think about from a very nice and new perspective, I would say. I quickly want to use the chance also to announce the next event. So next time it's December 7, yeah, same time again. So as I wrote also in the email today, I only write now Brussels time, since we changed between winter time and summertime. We always have 1 hour discrepancy. So if you're unsure, just look at Brussels time, and this is the time that we use. So next time we'll have Jörg Fröhlich from the ETH Zurich. And the whole session is called Quantum Events, Trees and Histories. That of course attributes to the ETH approach for quantum mechanics. And the title is Stochastic Emergence of Events in Quantum Mechanics. So we would be very happy to have you again and have a lively discussion in the end. And until then, I would say be well, take care and stay safe, and see you soon. And then I would say we end the
Thanks
session.
very much. Bye-bye.
Thank you very much.
Thank you.
And see you soon.
Bye-bye.
Bye.
Bye bye.